Okay, I think we'll get started. So today is a fun lab. We're going to learn about the comparator inputs and output, as we will do two different versions of that. One where we're comparing two input values, a very common situation in the laboratory, and one in which we're comparing one input value compared to an internal reference value, which also would be another important application in the lab. We're going to learn to set up the GPIO register. We're going to let some of the previous video on just making the LED blink, if you did go back and watch that, or if you're coming off of the our PIC12F675 series, that will be quite familiar. But we're going to run into two new registers that are common to the or that are not in the PIC12F675, but are now in the PIC12F675 and are related to the comparator feature of this microcontroller. All right, so we're going to do two parts to this lab, as I said, and just more schematically, we are going to look at this type of a comparator, and we're going to need to code that into the microcontroller, so we'll see that much more carefully here. And this differs just in 3 bits. What we define as 3 bits gives us 8 different ways of configuring the comparator. So we're going to do 2 of the 8, and you can practice around with the other 6, and we'll look at those in just a moment here. And then in part 2, we're going to just have one input. This will be on input pin 1, and this will be compared to a reference voltage. Now, what we're going to see here is not optimal. So what I've tried to do is have essentially just focusing on the microcontroller and not worrying at all about the electronic circuits. So what we're going to see with these comparators is that if we're close in voltage, then we're going to get so what we're going to do is have our LED light up or not, depending on what state the comparator is in. But we'll find a region there where the LED stays sort of dimly lit, and that's because there's lots of fluctuations just from the environmental noise that will cause it to periodically go to the other state of the comparator. And how you would handle that would be in the electronic circuit. You could do some noise damping, or at least some high frequency, drain off the high frequency noise with some capacitors. But to keep things simple and to keep things focused on the microcontroller and on the code, we won't worry about that. We'll have a comparator that'll work, but you would want to use a big swing of voltage rather than being really subtle. So it wouldn't work that great for, like, say, a temperature probe where you want a very sharp cutoff. You would have to do more than what we have. But what we will see is that under these conditions, the circuit is trivial and the code is trivial. So that's pretty neat. It kind of speaks to the power of the microcontroller. All right, so let's go in and start looking at the code, and we'll go through the data sheet as well. So let's go to here now, and let's look at the code. So this is all just the configuration bits. So we're familiar with that. Again, if you looked at the Lab 0 course, or the prelim lab where we're blinking an LED, we talk a little bit about this. I also talk about it in the series on the PIC12F675 microcontroller. This is just the include file that includes all the sort of background features associated with the with all the PICs, but with PIC12F675. And then this reset vector, again, that just needs to be there exactly as is in all of our code, just to start the program counter correctly, and so on. And then as the structure that I tend to like to have is main starts the program, then we'll do some stuff, and then we'll go into our main loop that the waiting, the microcontroller when it's doing its job would just be going through this loop the whole time. And what we'll see, well, actually we can look a little bit ahead here. Essentially there's nothing in the main loop. And so this is a, just shows how simple it is to use this comparator. But we do have to do a little bit of work up front here with programming in some of the bits. And so let's go through that carefully here. Now, in the structure of the microcontroller, we have two banks of registers, as we've talked about in previous videos. And so the first thing we're going to want to change is the GPIO register, which is in bank 0. So we do bit clear. The status bit number 5 tells us to shift to bank 0. Then, just for good measure, we clear the GPIO. And I should say not only the GPIO, but the CMCON register is also in bank 0. So we're in bank 0 here now. Again, just kind of good practice to clear the register when the program starts. Probably doesn't matter if that's there or not. Here's the important thing now. So this is to choose, and the last 3 bits here will choose the comparator. So let's take a look. Actually, I'm going to switch now. Unfortunately, I'm going to have to switch to this mode. And hopefully now you can see both the doc cam and the code. So what we're looking at here is 001. So that's down here. That's going to be output, comparator with output. There are some here with no output, so you want to be careful of that. So this is a standard comparator, but there's no output that comes out. And we want to see the output. We want to just light up an LED when one is greater than the other, and vice versa. So here we are. This is what sets that. So 001 sets that. We're going to also look at this one here, comparator with an internal reference. So that's what we'll do. Next, we'll just simply change that. So this binary, and I like to keep it in binary. You could certainly use hexadecimal, but this helps me go back and look at, I'll go back to here now, and it looks at this whole CMCON register. And this is what we're talking about now. We will talk about this in the next, in part 2, the inversion bit here. So in this bit, there's way more than you need to accomplish. So there's multi ways to accomplish the same thing. And so you could just find the one that works for you. In our case here, in this first part, we just want to compare 2 voltages. And we don't really care one or the other. We could just switch the wires, whether we change the output. But we could do that here with this C inversion here, but we'll just not worry about that for part 1 here. Okay, so we've now moved the working, move this literal, this is a literal, now put into the working directory. So this binary number is put into the working directory. Then the working directory is moved into this register. So it isn't until this step that this register has been written to, and now the choice of the comparator has been made. Now we have to move actually to bank 2 because we need to turn off the analog to digital. We want to pins are serving multi-purposes. There's digital input, comparator input, and then analog to digital input. And so the AND cell register is what controls the analog to digital. So let's look on page 44 here of the data sheet. And we want to set these last 4 bits to 0. So we're just going to clear the whole thing. That will just turn off, essentially. Now it says the digital I/O, but the CCOM is going to take precedence there. So this is going to turn off the analog to digital component of it. And so then we move our working directory to the AND cell. Now, we do need to have the bits turned on correctly. So we know that zero is an output, and so we want bit number 2 or GP2 to be 0 to be an output, and then 1 is an input. So we want 1 and 0 to be input. So regardless of whether you're doing a digital input or this comparator input, you need to turn the pins correctly, and so that's done by casting the correct 1s and 0s here in this binary, and then moving that to the tris IO. And then we come back to this. This line is not as important, but we'll come back to. Let's see. Yeah, this line will just take us back to bank 0. And then a couple of no operations, then we go into the main loop, and we'll just keep looping in here. And what will happen is the pinout for GP2 will be either 5 volts or 0, depending on the state of the comparator. So let's go ahead and bring in now the doc cam. And so let's look at this now. And I've got my PIC12F675 here, and I'm going to program. I've got this circuit all set up, so you can check out some of the other videos to see how to put this all together. But circuit is set up here now to program. So let's go to the MP lab again. Let's go ahead and go like this. So I've got the settings here, the power settings. I'm going to show you this here. Got the power settings for the PIC kit. Power, where is that? Well, let me see here. Power. So I've kind of learned the hard way of having the power on and working with the pins as not GPIO. I don't quite understand exactly why, but I try to power this with the PIC kit to do the coding. Then I'm going to take my PIC kit off. I always am a little bit worried too about supplying voltages when the PIC kit is on there. Hate to screw up the PIC kit. And I certainly make a lot of mistakes in the wiring, so could easily be done. So I'm going to take off the PIC kit, and then we'll put on the actual power for it. But for now, I want to power this chip with the PIC kit. So that's already set up. So you don't need to do that, and I've been able to like quickly run it with the PIC kit, but then I notice sometimes, on occasion, the microcontroller will get very hot. So I'm not completely understanding everything. So this is now. Let me switch here now to Comparator. Set as main project. Where is that? There. Set as main project. So we're looking here at Comparator 1. And this is now the main project here. So this is what's going to get compiled. Let me make sure everything's working correctly. So do a build. The build works. Now hopefully the writing of the chip will work. So do that. It's erasing, writing, and complete now. So like I say, let me actually go back here now to just the full screen. And hopefully you can see everything. So we'll take this off so we lose our power, but now I've got some power coming in just from a USB right plugged into the wall, and so I'm going to plug that in here, and then I'm going to bring in the voltmeter here, and I've got just 2 voltage dividers here. This is just 2 identical resistors, so let me look at the voltage here. Should be about 2.5 volts. And so that's the 2.5 volts. And we're going to compare that. So let's put this guy in one of the pins. Okay? And we'll compare that then to this voltage here, which we have control of now with this trim pot. So let me put it above. Let's go, say 3.9 or something. And let's put that in here. And, oops, not there. Let's see. Right here. Okay, so now you can see the voltage. So it's being compared to 2.5 coming from this black wire and this voltage divider, and then I'm going to adjust this now downward, and when we get below 2.5 we get, I think you can see here hopefully, the light comes on. So off, on. Now let me show you here how close we can get. So we were 2.48, I think we were. So let me try 2.58, and yeah, it's still off. And actually it's on. Maybe you can see this. It's very dim. When I put my screwdriver in place, then it is acting as a big antenna, and so we're fluctuating above and below that voltage. So now let's turn it below. So let's go to like 2.4. Okay, so that's on. That's still very good. So this is actually pretty sharp. I think we'll see what the internal reference, we won't get quite good, but very sensitive here. 5.1, it's off. And 4.1, it's on. So quite sensitive there. All right. So that's just the basic comparator. Let me go ahead and take these out here. And I'm going to actually just remove this wire because I always forget and then use that one, and I'm changing the trim pot and then nothing's happening. I'm wondering what's going on. Okay, so I'm going to take this out, and let's go back to the MP lab. Okay. So now I'm going to switch, and before I forget, I'm going to turn this to our main project, set as main project. And let's walk through now the part 2. So everything up here is exactly the same, just the configuration bits. This is all exactly the same. This is the same, so we're going to change to bank 0, clear the GPIO, move. Okay, so this is different here. So let's go ahead and look at this one. So the only difference here now is, let's go back to the comparator diagram. And this is this version. So the 011 is telling us that we're going to work with the comparator with internal reference and output. And this is interesting because we have to set now the internal reference. So let's take a look at that. So this is all the same now. We clear the AND cell, and I just got this new meter. I quite understand why it beeps at me over so often. Okay, so we clear the AND cell, the tris. Now let's go into the main loop here. And we do have to have something going on in the main loop now. So we have to be setting the VRCon register here, and that will supply the register the internal voltage. So this is on bank 1. So let's go. Actually, I should have shown this earlier. If I can find it quickly here. Yeah, so these are the banks on here. So GPIO in bank 1, and then I'm going to turn this off. And then CMCon in bank 0. So GPIO, CMCon in bank 0, then VRCon and ANCEL in bank 1. Okay, so what are we doing here? Well, let's look this up now. Let's look up the Vercon There we go. So what we're going to do here is we are going to tell with ones and zeros here what voltage we want as basically a percent of the voltage supply. And this, in order to give more range on that, you set it to either a high voltage, that would be something above about half, and then a low voltage, that'd be something below about half. We're going to go ahead and use the low range. So the VRR here is going to be set to 1. So that's this one right here. So that says we're using the low range. Then the bit over from that carries no meaning. And then the remaining 4 bits, we type in a binary number that will be a fraction of 24. So it'll be divided by 24. And then this factor, so we'll take that number divided by 24 and then multiply the VDD by. So you can see it goes a little bit above half. So we're going to go ahead and multiply 1010. So let's go ahead and calculate now the so I'm going to convert. Let's just sort of do this here. I'm sure you can all do it in your head, but let's do this here. So 1010 1010. Okay, that's binary. We'll convert to decimal. So that's going to be 10. Now let's take and we'll go 10 divided by 24 equals 0.41. Now let's measure, turn this back on again, and let's go ahead and measure our full voltage. So I'll turn this on and measure our full voltage. 4.994. So then I'm going to take this number times 4.993, 2.08. So that's going to be our reference voltage. So 2.08 volts. So let me go back and monitor the voltage that we're supplying. Now I do need to rerun this, so I'm going to unplug this power and plug in the PIC12F675, and now make sure that everything works. So building this, going to, and I think I'm on comparator 2, so part 2. So I'm going to dump this. Hopefully this will work. Complete now. So let me take this off. And let's plug in our voltage. And now we supply to pin 1 here. So let me make sure I got pin 1. Check my pin out here. I always forget. No, I put it in pin 0, so this is pin 1 here. Okay, so here we are at 2.4. So let me go, that's above. Now you can notice the, I'm going to switch here now so we don't need the code anymore. So maybe you can notice the light is sort of on there. Because we're getting that flicker, but we are above the voltage, and now I'm going to go down below the voltage, 1.9, and the light comes on. So we are comparing to that 2.08. And we see it go on and off with that. Now, this, let's try to remember here. Now, we are above the threshold and our light goes off, and we are below the threshold and our light goes on. Now, here we may really want to invert that. We can't just switch the wire position. So let me go back now to the full code. And let's go back and switch that. So that is going to be in CCOM. So let's go find the CCOM register. And we want this pin here, the C inverse pin. So that is going to be, where are we at here? So here are the modes, here are the 3 modes. Then this CIS, and here's the one we want. So notice it's 0. So that means we are output not inverted. So we are going to want to invert that now. So let's change that to a 1. And I will rerun this. So let me build to make sure that's okay. And looks like it worked. So now I'll take this off, repower it up. And notice our light is on now. So let me switch back to just full mode here. So light is on when we're over, and now when we go below 2.8, our light turns off. So we can see we've changed the high status of the output pin now so that it's high when we're above the threshold. All right, I think that is pretty much everything that I wanted to say about the comparators. So this is a great feature that we didn't have in our more primitive baseline microcontroller, the 10F200, but now in this mid-range controller, still very simple microcontroller, but has the comparator capability, which can be very, very handy in the lab. And like I said when I was at the board there, you can sharpen this by doing some high-frequency noise reduction by incorporating an additional circuit where some capacitors shunt that high frequency to ground, or maybe across the two leads of the comparator. All right, so that's it for this lab.